Welcome to Unit 7, Lesson 11 in Math 8, representing small numbers on the number line. We're going to visualize small numbers on the number line using powers of 10. And by small numbers, I mean really small numbers. When we're talking about a number line between 0 and 1, we're going to focus on something that's way back here, super close to 0. So we're actually going to expand this little point to something else. We're going to do that by looking first at this situation where we have Karen who drew a number line, and then Andre looked at it and says, that doesn't look right to me. So we need to explain why Karen is correct or explain how he can fix the number line. It's really important to recognize first off, what do these numbers actually represent? When we look at 1 times 10 to the negative fourth power, we need to recognize that as 1 times 1/10 raised to the fourth power, where actually that negative exponent represents a fraction or a reciprocal of the power that's being given, a reciprocal of the base. When we understand this value, it's helpful to understand that we start with 1, and when we multiply 1/10, we're actually moving our decimal one place value to the left for every time that we multiply by 1/10. So when we multiply there by 1/10, that's to the 1/10 to the first power, 1/10 to the second power, 1/10 to the third power, 1/10 to the fourth power. You can see that there are 4 powers of 10 that are moving this decimal, and we actually get out of this 1/10,000th. So 1 times 10 to the negative fourth is 1/10,000th. We can apply that same strategy to the rest of these. While I'm not going to write all of them, we can understand that the next one will be 2 10,000ths and 3 10,000ths, 4 10,000ths, 5 10,000ths, so on up here to 9 10,000ths. And then this one should be 10 10,000ths. Let's look and see what this looks like. 1 times 10 to the negative fifth power would be 1 times 10 to the negative fifth. There's negative 1, negative 2, negative 3, negative 4, negative 5. Now that I have a pretty good understanding of what my numbers are, I can make this analysis to decide is Karen correct or how he can fix the number line. And the first thing that I notice here is that the end of the number line to the right has one more place value to the right of the decimal than at the beginning. I know this is not correct because that number is smaller than this number. So this 10 to the negative fifth power should actually be to the left of 1 times 10 to the negative fourth power. It should be somewhere down here. Karen's mistake is with the number that he went to next. So Karen accidentally decreased when choosing 10 to the negative fifth. He should have used, hopefully you're already ahead of me, he should have used 10 to the negative third power. And by doing 10 to the negative third power, we recognize that we're moving into a value that's going to be greater than 10 thousandths. So we need to actually move, 10 thousandths. We actually need to move back one place value, which would put us into the thousandths place. And 10 to the negative third power will accomplish that for us. So if we went 10 to the negative third power, then we would see 0 and 1,000th, which is where we need to be as following the intervals here of increasing as we move down the number line to the right. So pay close attention today because, like I said, we are going to actually be looking at a very teeny tiny section of a number line between 0 and 1. So this number line here would actually just be a cross section that represents all of those values between, not all of them, just a few of them, from 0 to 1,000th down here at the right end. All right, when we go to compare numbers on a number line in small numbers, we are going to use what we saw before right here. We recognize that as we move to the left, just like we see in negative numbers on the negative side of the number line, as we get to smaller values, we recognize that we have smaller powers of 10. Do not mistake these powers of 10 as making a negative outcome because they don't do that. Remember, this is an indication of using a reciprocal. Rather than multiplying the number by 10, we're going to be multiplying by 1/10. Now, understanding that concept, if this is 10 to the negative fifth, then I need to get to a value that's going to be smaller than 10 to the negative fifth power, and that would be 10 to the negative sixth power. So what I will do with this one is I'm going to have to write pretty small to make sure that each of these can fit. So this will be 9 times 10 to the negative sixth, 8 times 10 to the negative 6, 7 times 10 to the negative 6, 6, 5, 4, 3, 2, and 1. And just like in the previous lesson, we're going to plot some points on the number line. When we see these values, this helps us to understand where to plot our points. So when we see this number in scientific notation, 6 times 10 to the negative sixth power, we can recognize that that point will be plotted right here. When we see 6 times 10 to the negative seventh power, we don't actually see that anywhere in this number line expressly, but we should recognize that that value will be back in this next section. So if we magnified this section here, we would see 10 times or 6 times 10 to the negative seventh a little more than halfway back to that value. Actually, I take that back. We would have that value in here actually in a smaller span. So we would have to take this piece of it and break it into 10 pieces. And then we would find that value in here of 10 pieces into a much smaller interval section. And we would see it probably somewhere right around here. But again, this is just an estimate because we don't have the exact value. Letter C might throw you off just a little bit. And the difference is right here is that decimal right here. This is what we call our finite decimal. Well, this value is not written to 10 to the negative sixth power. So it might seem a little confusing of where would I put 29 times 10 to the negative seventh power. We might be thinking that it's somewhere down in here, but the fact is it's not. Under scientific notation, this decimal cannot exceed, it cannot be 10 or higher. It has to be less than 10. It must be at least 1, but it cannot go over that. It has to be a single digit. For that purpose, we will move our decimal back one place value. So we're going to make this value 2 9/10 times 10 to the negative first power. And then we'll be multiplying by 10 to the negative seventh power. Excuse me, not negative first power, first power. So as I remove a place value here, I create a power of 10. And then I simply use product of powers to combine to make this 2 9/10 times 10 to the negative sixth power. This helps me to determine that point C will be right there on the number line. And then finally, we can do the same thing here. We see 7/10. Again, this value is too small to be scientific notation. It needs to be at least 1. So we will multiply this value by a power of 10. That means by removing this power of 10, I need to borrow a power of 10 from that value, making it a negative power of 10. I need to multiply this by 1/10, or excuse me. Oh, sorry, I thought I was going to have a sneeze. I need to multiply this by 10. In order to multiply by 10, I need to borrow a power of 10, which means that will put me into the negatives. That will be multiplied by 10 to the negative fifth. Again, product of powers tells me that same basis, I can add the exponents, making this 7 times 10 to the negative sixth power, or here on the graph. So the question is, which is larger, 29 times 10 to the negative seventh, or 6 times 10 to the negative sixth? Estimate how many times larger. We saw that this one was scientific notation. This one was not. Or excuse me, A is what we're comparing to C. We saw that 29 times 10 to the negative seventh actually became 2 9/10 times 10 to the negative sixth, compared to 6 times 10 and times 10 to the negative sixth. And we clearly see that this value of 6 being the finite decimal being larger when the powers of 10 are exactly the same is a greater value. So how many times larger? Well, 6 times 10 to the negative 6 power divided by 2 and 9/10 times 10 to the negative 6 power results in these values equal 1. So I don't have to worry about those. Some might call that cancels out. And 6 divided by 2 and 9/10 is approximately 6 divided by 3. So we're going to call that approximately 2 times larger. All right, I've talked a lot about scientific notation. I realize that that's a spot that's going to be kind of new. I've also changed the bullet point to an X. Typically in scientific notation, we use the times symbol written as an X because it distinguishes between the decimal value and the bullet point, and we don't want to see confusion with those pieces. Okay? So let's take a look at these next two values, say which one is larger then. As we look at these powers of 10, we have to understand that the power of 10 determines the place value where we're given. Now, while this place value right here says 10 to the negative 8th and 10 to the negative 9th, you might be tempted to say, oh, well, that has more powers of 10, so that one is going to be the larger value. Remember that negative powers follow the same rule of negative numbers. This power of negative 10 will be less than this power of negative 10 over here. So negative 10 to the negative 9th compared to 10 to the negative 8th, this value would be smaller. So 3 times 10 to the negative 9th power is less than 7 times 10 to the negative 8th power. Estimate how many times larger. You'll notice that I set this up in a division problem. So 7 times 10 to the negative 8th power divided by 3 times 10 to the negative 9th power. We use quotient of powers, or quotient here. 7 divided by 3 is going to be 2 and 6/10 repeated. So we'll call that 2 and 67/100. Nope, just kidding. This is going to be 2 and 1/3. So this will be 2 and 33/100. So we're going to have to say approximate times 10 to the quotient of powers. That would be 10 to the negative 8th minus negative 9, which would make this 1. And then we represent this piece by multiplying. So 2 and 33/100 times 10 is approximately 23 and 3/10. And so we would say that about 23 and 3/10 times larger. All right. Moving on to the next one, talking about atomic scale. This is what we've been working with, little teeny tiny numbers. So now we're magnifying to an even smaller value. The radius of an electron is about 3, I don't know what that one would be. And because of that, it makes it hard to write it as a fraction. So write this number as a multiple of a power of 10. Decide what power of 10 to put on the right side of this number line and label it. So I think the first thing that we should do is let's put it into scientific notation. We come all the way down here to find the first digit that is not 0, or the non-zero digit, and that becomes our leading digit for the finite decimal. Now we count the place values that I have to move backwards from this. So this is going to be times 10. Recognizing this is a really small number, we will be using negative powers of 10. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 powers of 10. So this will be times 10 to the negative 13th. One strategy that I like to use when counting these is I will break my numbers up into groups of 3 just to help me with counting those values. So decide what power of 10 to put to the right side of this number line. Remember, we need a power of 10 that will be just larger, 10 times larger than 10 to the 13th. So we should have 10 to the negative 12th power right here. There's not enough room in that box, so let's go ahead and put 10 to the negative 12th power. And then these values down in here, we could go ahead and label the tick marks as multiples of a power of 10. So 1 times 10 to the negative 13, 2 times 10 to the negative 13. You get the point. I'm losing space, so I'm going to skip over some of these. Okay, and then we're supposed to plot the radius in centimeters on the number line. We know it's 3 times 10 to the 13th, so we would see that point right there. All right. The mass of a proton is another big number here. And again, I don't know how to write this. And that's the purpose for scientific notation. It's numbers that are so incredibly small that we probably have a name for them, but it's not something I know off the top of my head. You're welcome to go and research it. But what I do know how to do is do this. I know that that decimal in scientific notation has to move all the way down here between the leading digit 1 and 7. I can't put 17 here because that won't be scientific notation. Scientific notation states that when we take a value, we have d times 10 to the nth power, where d, the finite decimal, has to be greater than or equal to 1 and less than 10. That's the rule that follows. N could be any number, any digit except for 0, and where n does not equal 0. So now what we're doing here is we're multiplying by 10, remembering that this is a value less than 1, so we have negative exponents here. So now I'm going to break this up. There's 3, 6, 9, 12, 15, 18, 21, 24 powers. So I'm actually multiplying by 1/10, 24 times to make that happen. If I want to go ahead and work this out, decide what power of 10 to put on the right side of this number line and label it, well, here we go. I need a number that is 1 power of 10 greater than 10 to the negative 24th. So when we look at that power of 10, I need to know the power of 10 that exceeds 10 to the negative 24th. When I look at a number line, I would know that 10 to the negative 25th is less than 10 to the negative 24th. So I need my number line to represent up to 10 to the negative 23rd power. Again, getting our values of negatives are increasing when we see the numbers, the values decreasing. So again, the same type of thing. Let's go ahead and label these. This would be 1 times 10 to the negative 24th, and 2 times 10 to the negative 24th, and 3 and 4 times 10 to the negative 24th. For the sake of time, I'm not going to label everything, especially knowing that 1 7/10 will be a little more than halfway. That would be where the mass of the proton is. Plot the mass of the proton in grams on the number line. Keep in mind that when we're looking at this number line, these are incredibly, incredibly, incredibly small numbers. And so we've taken a number line, the number line that's between 0 and 1, and we have magnified to a point where it's going to look like we're almost on the 0 line. As we look into this, our next step with this, it says plot A on the zoomed in number line, or the point A on the zoomed in number line describes the wavelength of certain X-ray in meters. Write the wavelength of the X-ray as a multiple of a power of 10. Well, we're looking at a value that is really, really small. In fact, 12 place values less than 0. So we've multiplied by 1/10, 12 times. And now we're magnifying this little segment right here from 6 times 10 to the negative 12th to 7 times 10 to the negative 12th. With these values, I need to be thinking that we're already in the same place value. So what I need to do is go ahead and look to the next place values that fall between 6 and 7. And that would be place values such as 6 and 1/10 times 10 to the negative 12th power, and 6 and 2/10 times 10 to the negative 12th power, 6 and 3/10 times 10 to the negative 12th power. And just for, again, sake of time, that'd be 6 and 4/10, 6 and 5/10, 6 and 6/10, 6 and 7/10, 6 and 8/10, 6 and 9/10. So down here, times 10 to the negative 12th power. And then as I go ahead and move on to another 10th more, then I get to 7. So hopefully that makes sense how I got it to there. When I write the wavelength of the X-ray as a multiple of power of 10, I look right here at A. I see this as 6 1/10 times 10 to the negative 12th power. And just for the piece of this is exactly what I want to see, a multiple of a power of 10. This is what that number would look like in standard form. I would start with 0, and then I count my place values until I get to the 6th. This 6 would be the 12th place value after the current decimal. So here is times 1/10, 10th, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 1. These values right here, there are 12 powers of 10 that represent those 12 place values. This value right here, as we recognize that this is this problem right here, represent the powers of 10 that be inside of this scientific notation. That's been a lot for this lesson, okay? There are some huge factors that I need you to represent out of this. We'll see those here briefly in the lesson summary, and I'm going to summarize some things that are not actually here to hopefully help you with your homework. So the width of a bacterium cell is really little. It's 2 times 10 to the negative 6th power. If we wanted to plot this on a number line, we need to find out which 2 powers of 10 this falls in between. And so our number line would actually come down to a number line that's really, really small. We notice that the right side is labeled that of 10 times 10 to the negative 6th power is 10 to the negative 5th power. The power of 10 on the right side of the number is always greater than the power on the left, just like any other number line. This is true for all positive and negative powers of 10. With this understanding, I want you to recognize a couple of things. Let's take a couple of examples. This number right here is 4 hundredths. When we write this number in scientific notation, we begin with the power, or with the leading digit 4, and then we multiply by 10 to a negative power. Anytime we have a number that is less than 1, we are using a negative power. That negative power will always be the value of moving this decimal to the right side of that leading digit. And so in this case, we would see 2 place values to the right in order to make this a 4. So I would have to multiply this by 1/10 2 times. If I had a number such as 0 and 0, 0, 1, 0, 2, this number is 100 200 thousandths. That's how we say that number. When we write that number in scientific notation, we write that number as come across to the first digit, first non-zero digit. This is what we call the leading digit, 1, and include the next digits. I know that there's a 0 here, but there's also a 2. 1 and 2 hundredths times 10. Look back to how many place values it took to get past the leading digit, and recognize that as a negative power of 10, which would indicate that we're multiplying by 1/10 of this value right here. So 1 and 2 hundredths times 1/10 would bring the place value back 1 times 1/10, times 1/10 to bring it back to those values. I hope that that's a good start for you. Scientific notation is something that can be really fun when we understand where it's at. Remember, the main rules go like this. You have D times 10 to the nth power, where D is a finite decimal that follows the rule that D must be greater than or equal to 1. So it can't be 0, it cannot start with a 0, and it has to be less than 10. So it cannot have 2 digits in front of the decimal. These digits, the only digits that you're allowed to use in scientific notation, are 1 through 9. Okay, the value of n can be anything except 0. I really hope that's a good start. I hope this helps you out with today's lesson. Thank you for working so hard. I know this is a really long lesson, but I hope you got something great out of it. Let me know what I can do to help. Take care now.